Learning through physical interactions plays a critical role in human cognitive development. BusyBoard, for example, is a kind of toy designed for kids to acquire fundamental manipulation and reasoning skills. A BusyBoard comes with the following advantages. First, the rich sensory feedback encourages children to actively explore and interact with the board. In addition, the observed inter-object function relations, for example, pressing a switch turns on a light, facilitate the development of reasoning and task-solving skills. Inspired by the toy, we built a BusyBoard environment in simulation and train an embodied agent to learn to interact with objects, reason about inter-object function relations, and plan for goal-conditioned tasks. We also demonstrate that the skills learned in simulation can transfer to real-world scenarios with robot interactions. Each BusyBoard environment is composed of trigger objects, responder objects, and the inter-object function relations. We procedurally generate BusyBoard environments with diverse appearances, including different board color and texture, object instances, object layout, and the underlying relations. We propose a self-supervised learning pipeline, BusyBot, for an embodied agent to learn three fundamental capabilities: interaction, reasoning, and planning. In the interaction module, the agent learns an interaction policy to efficiently interact with objects and explore novel states in the BusyBoard environment. Given a visual observation of the board, the agent obtains the interact position and direction by jointly training a position and direction inference network. This task is particularly challenging for objects with small displacement upon interaction, whose appearance change can be subtle even under effective actions. However, in the BusyBoard environment, the triggered responder effect can amplify the visual feedback and assist the agent to learn good interaction policies. In addition to an object-level interaction policy, the agent also needs to acquire environment-level reasoning skills. In the BusyBoard environment, the task is to infer inter-object function relations. Using the trained interaction policy, the agent first interacts with the BusyBoard for several steps and collects an interaction sequence. Given the interaction sequence, the inference network uncovers the inter-object function relations. When conditioned on the current observation, an action, and the functional relations, the dynamics network predicts the future state. The inference and dynamics network are jointly trained under the objective to make correct future predictions. Finally, by combining the learned interaction and reasoning skills, the agent is able to plan for goal-conditioned tasks. During goal condition planning, the agent first infers a set of action candidates for the current scene using the learned interaction policy. Meanwhile, the agent interacts with the board, obtain an interaction sequence, and infer the inter-object functional relations with the inference network. Finally, given the current visual observation and each action candidate, the dynamics network predicts the future states. The action that has a predicted future state closest to the goal will be selected for execution. We test the trained interaction module on a real-world BusyBoard, which consists 3 switches as trigger objects and 3 LEDs as responder objects. The result shows that our model is able to identify the proper interact positions and directions given a real-world visual observation. We also evaluate the reasoning module on the real-world BusyBoard. By looking at the inferred graph labeled with red edges and the ground truth graph labeled with green edges on the right, we can see that at the beginning, the inferred relation graph contains a lot of additional edges. As the robot interacts with the BusyBoard for more steps, the graph refines and uncovers the correct inter-object function relations. We also manually modify the real-world BusyBoard to obtain more configurations of inter-object function relations. And our model performs well on uncovering the inter-object function relations for all these additional configurations. Thanks for watching.